dqf2 by introducing the relative coordinates, that is r double dot r is equal to r2 minus r1. The second virial coefficient which was obtained yesterday becomes 1 minus 1 by 2v dqf1 dqr e to the power minus beta into phi r minus 1. And this is nothing but if you perform this integration, one of the integrand is performed, this will be e to the power minus beta phi r minus 1 4 pi r square dr. When you perform such integration, then you will obtain the virial coefficient v2, which is 1 by 2v double integration e to the power minus b phi 2. And on simplification, if we write the step involving phi 1 2 and phi 1 3, then in that condition you can calculate the third virial coefficient. This is the aim of cluster integral. When you know the second virial theorem, you can calculate the third virial theorem, and this third virial coefficient v3 is nothing is equal to 1 by 6v triple integration. See, this is double integration. v1 is single integration. Third virial coefficient is triple integration e to the power minus beta phi 1 2 e to the power minus beta phi 2 3 e to the power minus beta phi 3 1 minus e to the power minus beta phi 1 2 minus e to the power minus beta phi 2 3 minus e to the power minus beta phi 3 1 plus 2 multiplied by the volume, the integral factor dqr1 dqr2 dqr3 is the total volume for the three virial coefficients. And after simplification, you will get equation 13.2, that is 3 volume times third virial coefficient is the triple integration e to the power minus b phi 1 2 minus 1 e to the power minus b minus beta phi 2 3 minus 1. Initial this was beta into 1 minus e to the power beta phi 3 1, the volume element dqr1 dqr2 dqr3. And you can also simplify this, and finally you will get minus 1 by 3b triple integration e to the power minus beta phi 1 2 minus 1 beta phi 2 3 minus 1 e to the power beta phi 3 1 minus 1 dqr1 dqr2 this one. Now we know the molecular forces are short range. So what are the features of V3? Third virial coefficient feature, when you study it, we can have some knowledge regarding our cluster integrals. For that reason, we will tell the molecular forces are very short range. So they have effective contribution to the integrals, and the integral value, the integral come from the value of r, which is the order of 30. We can see V2 is the outcome of two body effect, V2, and V3 is the outcome of triplets. V2 arises due to doublet, V3 arises due to triplet. Now we involve a function Fij known as Mayer's function. You will know later. We will define a function, Mayer's function, e to the power minus phi by k beta t minus 1. When you define this function, then we say for a perfect gas Fij is equal to 0. As the matter of conjecture, we can say this function, you can say the Mayer's function versus your distance, the graph looks this one up to this point. You can note there is a node at this point and this point represents minimum value. As this graph is the for Mayer's function f. We have already defined Mayer's function fij e to the power minus phi ij by k beta t minus 1, and the Mayer's function we can write in this manner: e to the power minus beta phi is equal to e to the power minus beta sum over phi ij e to the power minus beta phi ij means phi 1 2 plus phi 1 3 plus phi 2 3 plus 4. What is phi? Phi is the sum of phi ij. That is e to the power minus beta 1 2 e to the power minus beta 1 3 e to the power minus beta 2 3, which is, this is your Mayer's function, that is f12. Since f is your 1 minus this one, so 1 plus f12 is e to the power minus beta 1, and 1 plus f13 is e to the power minus beta phi 1. 1 plus f23 is e to the power minus beta 523. So now we can expand e to the power beta in terms of Mayer's function, and it comes around equation 13.6, that is 1 plus summation fij plus summation fij fki plus so. In this manner, when we expand the Mayer's function, which is related to coefficient phi, the function is expanded about the terms of phi r, and for large values of r it has finite values, and we can suggest we can express it, we can highlight it in terms of cluster diagram. How it is possible to use this diagram? In order to use this diagram, cluster diagram, we have take the simple example. What is a cluster? Cluster means combination of some points. Suppose a cluster is created by means of similar, say 10 schools constitute a cluster. Here we will consider the particles or molecules. 2 molecules, they constitute a cluster. 3 molecules constitute a cluster. And the diagram involving them is called cluster diagram, which can be explained by your Mayer's function as well as third virial coefficients. You can find here, this is a cluster diagram of 2 molecules. This is first molecule, this is second molecule, and we represent it as F12. This cluster diagram is represented by a line, and this schematic diagram is F12. That means the molecules 1, 2 form a cluster, and F12 is the integrand, or which is called Fij, and the integrand is performed about del R1, del QR1 and del QR2. Now you go to next picture, cluster of triplet, 3 molecules. If you have 3 molecules, 1, 2 and 3, this is called cluster of triplet. Now you can you can consider the third virial coefficient for which you can draw cluster diagram. What was our third virial coefficient, which was discussed in 13.3? That was B is equal to minus 1 by 3V F12 Mayer's function. This is F12 represent Mayer's function between cluster 1 and 2, molecule 1 and 2. This is molecule 1 and 3. This is molecule 2 and 3. dqr1, dq integration is dqr2, dqr3. So we involve 3 particles here, and in these 3 particles we can have 3 topological equivalent cluster diagrams. How? First particle may be here, second particle is here, third particle is here. This is one probability. Another probability is first particle is here, second particle is here, third particle is here. This is another diagram. Another probability, you can have one is in its place, 2 and 3 they are connected here. Here there is open space, here base is open, here other side is open. So 3 possible diagrams are possible, that is called cluster diagram of triplet. And these are well defined by virial coefficients V2 and V3. So we can say for interacting system, the cluster diagrams are represented by the virial coefficients in general, in not V2, V3, in general, this Vj is 1 by j factorial V integration Si2 up to j plus 1 and integrand is dr1 dr2 up to dj plus 1. Here S12 represents sum of all products of f functions, means Mayer functions, that connects the molecules this one. The connections are such that any one point is removed along with all the lines linked with the point, we still get connected graph. Such diagrams are called doubly connected. A diagram ko ame kahiba double connected. Then what is double connected diagram? Double connected diagram means two particles are connected by a line. Suppose 1 and 2 are particles, then we can say S12 is a double connected diagram which can be represented by, say, some constant H2. And when you consider S1 to 3, this will be H2, and the two Mayer's function F23 and F31 will be multiplied to make it topological equivalent. So what is topology? Topology means, topology relates the parts of something are organized, they are connected. Topology means if we have different molecules, their parts can be connected, that is called topology, and the diagram corresponding to it is called topological diagram. Suppose we will use the word equivalent. Topological diagram means equivalent diagrams. Suppose we have 4 points, 1, 2, 3, 4 represented in this manner. 1, 2, 3, 4. 4 points are vertices of a square. So its topological diagram can be doubly connected. 1 is connected to 2 is connected to 4, 4 is connected to 3, 3 is connected to 1. So this is the topological diagram of, or you can say this is a cluster diagram of 4 particles. So what is the other way? The other way is, this is 1, 2, 4, 3. You can have 1, 3, 2, 4, 1, 4, 3, 2. So in this manner, you can have equivalent diagrams. And these equivalent diagrams are called cluster diagrams, which clearly explains the virial coefficients with help of the Mayer's function. Suppose one example is asked, draw the star of 4 particles with 2 diagonals. Represent here, what you find, the diagonals may be 1, 4 or 2, 3. Here it is 1, 2 or 4, 3. It is 1, 3 or 4, 2. So you can have to draw the star diagram of 4 particles. Either you can have 1, 2 or you can have 2, 1. Then you can say these diagrams can be drawn in this manner. If P denotes number of points and K is the number of lines, in case of a square, 4 particles, particle points are 4, and K is the number of lines. How many lines are connected? Say K is equal to 4. then the nature of the graph will be this one. When P is equal to 2, K is equal to 1, this is the graph. Here M is a single line probability. M is the tabular form. You can say in a tabular form for P is equal to 2, 3. And P is equal to 2, you can find P is equal to 3, you have K is equal to 2, or K is equal to 3, you have K is equal to 2, here K is equal to 3, you have this type of diagrams. So these diagrams are cluster diagrams. Now, how these cluster diagrams are connected to the integral space? This, in order to represent these cluster diagrams in integral space, we have to recall the configuration integrals, for which we must know the partition function. So earlier we know the partition function. Remember in 12.14 equation last day, we know this partition function Zn is the integration sum over all the products where I is less than j, 1 plus Fij, dqr1, dqr2 up to dqfn, which is in terms of Mayer's function 1 plus summation Fij plus summation Fij fkl plus 1, and the integrand is up to dqr1, dqr2, dqn. Now, the number of particles involved in this cluster, this is a cluster, the number of particles involved in this cluster, if it is n number of particles, then this is n particle graph. It is 8 number of particles, this is 8 particle graph. So you can say, if it is 8 particle graph, XA, then it will be F12, F57, dqr1, dqr2, this one, or you have F34, F36, F78, this is XB. So this can be 8 particle graph, 1, 2, 3, 4, 5, 6, 7, 8. Here this is 1, 2, this is 3, 4, this is 5, 6, this is 7, 8. And these clusters from 1 to 2 and 5 to 7, what you have to consider here? F12. F12, this is 1, 2 connected cluster. F57, this is 5, 7. So when you take XB graph, this is F34 means the line will be here. F36 means the line will be here in this manner. F28 means the line will be 2 and 8, this one, straight line. So in this manner, the cluster diagrams are drawn. And the cluster diagrams are related to the configuration space. Let us have some distinct parts. You have 1, 2 and 3, or you can have 1, 2 and 3. So in this case, you can connect the line 1 and 2 and you have a dash after this is 3. In this case, you have 2 can be connected to 1 and 3, they are identical or they are equivalent or they are topological diagrams. Suppose we can express this in terms of another method. If we have these 8 integrands, this is 1, 2, 3, 4, 5, 6, 7, 8. If we consider another 2, up to this we have 8, another 2, 9 and 10, then the cluster diagram can be function F12, F35, F78, F79, F710, then F980 or F89. So we can say in this manner there are large number of clusters, and we say total partition function of n particle cluster is the sum of all distinct n particles in the graph. Now we will focus on I cluster. If we have I number of particles and we connect each of the particles, then this is called I cluster. You can see this is 1, 2, 3, 4, 5, 6. So you can connect 1 to 2, 1 to 3, 1 to 3 can be connected to 2, 1 can be connected to 4, 4 can be connected to 5, 5 can be connected. Then for this graph, the clusters are, remember, this is F1, F13, remember, F13, then F14. Here you find, for a particular graph, how you distinguishing. And this is F23, this is another one. Then F46 and F56. So how many? 1, 2, 3, 4, 5. So this is DQR1, DQR2 up to DQR5, because there are 5. And for the single integrand, this will be, the volume will be DQR6. There is one more. So the cluster integral for first virial coefficient, that is B1, which is a function of this, is 1 by I factorial into the normalization factor lambda to the power 3 I minus 1 into V. Remember, this one is a dimensionless term and it is finite in nature, such that this limit V tends to 0, V1 Vt is V1t. And in this manner, you have second virial coefficient can be represented in cluster diagram like this. V2 is 1 by 2 factorial lambda cube V between particle 1 and 2, the cluster diagram or cluster integral, which is 1 by lambda cube 2V dqr1 dqr2 f12. This is your second virial theorem, second virial coefficient. And the third virial coefficient, V3, that is 1 by 3 factorial lambda to the power 6V, remember 6V, that is 1, 2, 3, 1, 2, 3 plus 2, 3, 1, and this is 1, 2, 3. These four possibilities are possible. So this is called I cluster diagrams. Hence we can conclude that there are in general many ways to form I cluster. So if I number of particles, here I is 3, you can have 1 to 3 or 1 to 3 or 1 to 3. In this manner you can generalize them and you can draw I clusters. So we say Zn, which is the partition function for n particles. For I cluster, there are mi lines, which is total sum of the lines is S, or which is a function of mi. Now we will involve M1 numbers of 1 and M2 numbers of 2 clusters. If you have 2 clusters, this is M1 factor, this is the 0 to 0, this is the 0 to 0, these are M2 factors. For M1, this is 2, for M2, this is 2, 2. For M3, this is 3, 3. Similarly, for M4, this is 4, 4. In this manner, we can arrange the cluster diagrams. And what is our conclusion from this cluster diagram? Each graph is an integral whose value is independent of the ways in which the circles are numbered. So SM1 is the product of sum over omega and the value is not infinity. The former bracket indicates that mi number of clusters are I clusters and whose permutations does not lead to new graph. If we consider a sum of I clusters, a permutation of the particle, it does not lead to new graph. Hence, we can expand the cluster equation. How can we expand the cluster equation? Now, this is the way ZnVT. This is partition function for microcanonical ensemble in classical state ZNVT is dqr1, dqr2, dqrn, which can be written in terms of your multiplied by 1 plus f12 Mayer's function between 1 and 2 cluster, Mayer's function between 1 and 3 cluster, in this manner, where your QNVT, that is canonical partition function, is 1 by n factorial lambda to the power 3n ZNVT. And on simplification, you will find grand canonical partition function sigma ZVT is summation mi is 0 to infinity, mi is this one, up to 1 by mi factorial v z v1 aq to the power m1, 1 by m2 v by aq z square v square m2. In this manner, if you proceed, you will finally get the partition function takes the form sum over continuous product I is 1 to infinity e to the power v1 z v by lambda cube, and 1 by v log n is 1 by lambda cube v1 z factorial. So under v tends to infinity, p by kt will be 1 by lambda cube vi zi, and n by v is 1 by lambda cube I b1 zy. Hence, we consider that cluster expansion are possible with the help of Mayer's functions, and we can eliminate them. In this chapter, we found that the summary of this chapter, the cluster integrals are very much essential to obtain virial coefficient in a simplest manner. And the Mayer formula is very much essential to obtain the virial coefficients, that is Fij is e to the power minus phi ij k beta t. Now, the cluster diagrams primarily provide a tool for determining various integrals involved in virial coefficients. S2 to j plus 1 plays a crucial role for determining virial coefficients. Topologically equivalent cluster diagrams are called stars. A cluster diagram is referred as n particle graph, whose partition function Zn is sum of all distinct particles, and the first virial coefficient is dimension v1 vt is dimensionless, and it represents a finite number. The second virial coefficient v2 is represented by this diagram. This diagram between 1 and 2 particles, and the third one is represented by this plot we have seen. Then we have calculated P by Kt and the number of particles per unit volume. So one thing we conclude, that whenever the topological diagrams are introduced, it becomes easier to calculate the virial coefficients. And the virial coefficients, partition function of canonical, grand canonical and microcanonical ensemble, that is Zn, Qn and sigma n, are possible to calculate easily with help of these cluster integrals. This is all about unit 13. Then we will focus on correlation and strong scattering, that is unit 14. So, you know scattering in your, you have read scattering in BSc, so many Rayleigh scattering, so many scattering you have read. You have read X-ray diffraction there. The scattering comes from this concept. before reading scattering, why the particles are scattered in different ways. Their energies must be different. Why energies are different? Because there must be different fluctuations. So we must have idea regarding what are fluctuations. You know, in case of kinetic theory of gases, the phenomenon of fluctuations are more necessary because the molecules, though assumed to be identical, but they are not actually similar for different gases. So we characterize them by the most probability distribution function. We consider the ensemble average. As a result, we are able to calculate the fluctuations. So let us take one first line equation, 14.1 equation. Suppose we have a variable x. Then how can you calculate its fluctuation? The fluctuation is represented as delta x. X fluctuation, small value, x changes to x plus delta x. So delta x is the fluctuation. How can we represent this fluctuation? Now delta x is x minus average of x. So small delta x in equation 1 is this one. Delta x is x minus average of x. This average, or you can say mean value of x. Now, if delta x is simple fluctuation, then what is mean fluctuation? Mean fluctuation is the average of delta x, this one. This is simple fluctuation, delta x. Mean fluctuation is the average of delta x, which is x minus x average, which is the average of x minus x average, which is equal to 0. Now, one is fluctuation, that is delta x. If average of delta x mean fluctuation, if average of delta x square, this is called mean square deviation, or fluctuation which corresponds to mean square deviation. That one is delta x square is x minus is the average of x minus x average square, which is x square minus 2x x average plus x square. And this gives rise to the strength of the fluctuations is measured by the equation 14.3, that is delta x square by mod x square. So the mod x square factor is divided to make the quantity dimensionless. Now we will discuss fluctuations in different ensembles: canonical ensemble, grand canonical ensemble, and micro canonical ensemble. Then you come to the feature characteristics of canonical ensemble. In canonical ensemble, temperature, volume, and number of particles of a cell remains constant. When TVN are constant, then you can automatically say, when TVN are constant, you can say what changes and the energy changes. Electric variation is in square. This is canonical ensemble. Average of E square is En square e to the power minus En by k beta t by e to the power minus En by k beta t. So the partition function for canonical ensemble is Qn is the exponential minus beta En. What is beta? Beta is 1 by k beta t. Now here this is E square average, mean this is the average of E, that becomes minus 1 by Qn del Qn by del beta, and E square average is 1 by Qn En square e to the power minus beta n. Hence, when you find this one, you can find the average pressure in this manner. What is fluctuations in pressure? You have read pressure is 1 by Qn. Qn is your canonical ensemble partition function. Is the sum over I particles Pi e to the power minus Ei by k beta t. And the product of this into Qn gives it minus del Ei by del V, this factor, into e to the, for pressure we use minus del Ei by del V into this. When you solve this, you take partial derivative and solve it, you will obtain what is the average value of pressure, that is Q inverse. Q stands for partition function, sum over I del Ei by del V e to the power minus Ei by k beta t. On further simplification, we arrive at a result that is average of sigma p square. This is the fluctuation in pressure. We consider pressure here. This is the value of pressure, mean pressure. We calculate by using canonical methods of partition function. We calculate the fluctuation delta p square as k beta t del expectation del average of P by del V when the number of particles and temperature remain constant plus average of this mod of d square E by dV square. We evaluate this for a perfect gas, and by using this expression we can calculate the fluctuations in a canonical ensemble. So fluctuations in canonical ensemble, we can calculate fluctuations in pressure, we can calculate fluctuation in energy, we can calculate fluctuation in specific heat Cv and Cp, and we can deal with the actual fluctuation measurement we can deal with. Similarly, when you consider grand canonical ensemble, the fluctuation occurs in a number of particles, and in this case the mu mu remains constant. So the number of particles is the order of n to the power minus half, and the fluctuations, if we say n is 10 to the power 22, then the minus 22, the fluctuation will be 10 to the power minus 11. Sorry, if n is 10 to the power 22 particles in a grand canonical ensemble, then you will find number of fluctuations in that case is n to the power minus half, that is 10 to the power minus 11. So fluctuation becomes so large in grand canonical ensemble, it becomes very difficult to note the fluctuations, and the fluctuations are significant in the neighborhood of liquid gas. When liquid is converted to gas or phase transition takes place at critical point, then the fluctuations are more. If you consider isothermal compressibility, then at critical point where density is low, the fluctuations of the system are regarded as density fluctuations, and due to large scale density fluctuations, light is scattered or scattering of light takes place. This formula, when fluctuations of a system is very large, that means number of particles are 10 to the power 22, fluctuations are order of 10 to the power minus 11. That means if you have, as an example, 1000 persons in a meeting and 500 persons create fluctuations, so the meeting will be disturbed. Not only disturbed, but a large scale disturb. What happens? The waves generated due to motion of 500 persons within total of 1000 persons will create a wave. What type of wave it may be? Similarly, due to fluctuations of the molecules inside it, large amount of light is scattered, and this is called critical opalescence. Question asks, 2-mark question, explain what is critical opalescence of light. Now the scattering, it is a phenomenon. Critical opalescence is a phenomenon of scattering of light, which arises due to density fluctuations in a grand canonical ensemble. The fluctuations are also take place if you consider microcanonical ensemble, where EVN are constant, energy, volume and the number of particles are constant. Then by using probability interpretation method and gives hypothesis, Einstein suggested to make a relation between entropy and thermodynamic probability. So by Taylor's series, we can equate them, and the fluctuations can be 1 by n times. So both the grand canonical ensemble and microcanonical ensemble, we have not considered the fluctuations because we have avoided, say, calculation of these fluctuations, because its number is very large and very less respectively. So, how can we find fluctuations in those cases? Now, we have to consider a function known as correlation function. What is correlation function? Why we need correlation function? And where correlation functions are applied? Let us define, but take an example of fluid motion of n particles. If you consider fluid motion of n particles, then nr can be written as I is 1 to n, this by equation 14.11, that nr by Dirac delta function I is 1 to n delta r minus ri in 3 dimensions. Here 3 is not a power, you cannot write delta q, that is in 3 dimensions. That means it has 3 spatial components. So correlation function is defined by the equation nr is I is 1 to n del phi r minus ri, and the nr is a time dependent function. Correlation function is a time dependent function, but in equilibrium condition we only in equilibrium case, what happens, we are never bother about the time dependence. Now we can rationalize this correlation function. This correlation function in short form written as CF. When you take the average of NR, we obtain its real value by using Green's function method. Let us consider two particles whose positions are at r and r dash. R is one, r dash is the other one. Then we can, in that case, or x, y are two variables which represents. Then we define the correlation function Rxy, this one, as correlation of Vxy by sigma s sigma y. These are standard deviation. Standard deviation of x, x plus sigma x, and x plus sigma y. Now, these are defined as correlation function Vxy will be 1 by n summation I xi minus x average into yi minus y average. So sigma n is equal to sigma x is root over of summation I xi minus x average square by n. Sigma y is equal to root over summation I yi minus y average square by n. Hence, by Green's method, you can have a pair of correlation function, or simple correlation function is represented as G R R dash, another correlation function, that is NR minus NR average into NR dash minus NR dash average. And you can say this N minus NR dash. So the form of correlation function in the first it looks like this one, NR dash, it is summation I is equal to 1 to n, j is equal to 1 to n, del 3 r minus ri, del 3 r dash minus rj. In the RHS of above, there are two kinds of terms for which I is equal to j. When I is equal to j, the Dirac delta function term becomes del 3 r minus ri, del 3 r dash minus rj took the form r minus r dash minus rj becomes equal to k del 3 r minus r dash. Now, using the expression k is equal to 1 by v and n is equal to n by v, the correlation function can be written as, in terms of this Dirac delta function n delta 3r minus r dash, that is gr minus r dash is n delta 3r minus r dash plus n square. We introduce a gamma function here, which is a dimensionless function. When you consider Fourier transform of this function, the Green's function, f k r is dq of e to the power I k r f r. So here integration is, and by applying Green's function technique, you can find gk is n plus n square gamma of k. Gamma is a dimensionless function. You can obtain this gamma k c bar k plus n c bar k into gamma k. And remember, this 1 by gk is 1 by n minus c bar k. This is correlation functions. So what is physical significance of correlation? Why correlation functions are very necessary? First one is, if we consider a homogeneous isotropic classical gas, then there exists a potential energy between these two particles of such gas. But for two-body interaction, you can consider this one. So potential energy basically represented by W here. W is equal to sum over I, sum over j, I is not equal to j, phi, Ri minus R0, phi is a function of mod of Ri minus R. Simple formula that potential energy U is minus grad phi you have calculated, which is sum of this phi is a function of R. And using correlation function, you can find the average potential energy per particle. This is total potential energy, and average potential energy per particle is 2 pi n times integration 0 to infinity dr r square gamma r phi. Now, how can this correlation function, if we correlate it with the thermodynamics, then it will be easier to explain its physical significance. That is, n minus n average square is kt by beta v n square, which is kt by 1 by k beta t v n square v sman kt v n square k beta t. And when you solve this one, you will obtain this expression, that is kt n square k beta t is dqr gr. What does it show? The correlation function is linked to kt, that is isothermal compressibility. So correlation function is related to isothermal compressibility. Now the correlation function of a fluid, when you calculate, then you will find the, due to scattering, the electromagnetic radiations arises. So correlation function clearly theoretically defines how electromagnetic radiations are possible due to scattering. So next heading will be correlation function and scattering. In order to study that, let us consider a plane electromagnetic wave characterized by a wave vector k. We have a plane electromagnetic wave characterized by wave vector k incident on the fluid. The intensity of the scattered wave, remember k is the wave vector. So intensity of the scattered wave will be k prime, that is small k minus big K. And this is given by equation 14.32 of your book, that is L is a function of K, is the average of mod of summation of I is 1 to n, total number of particles, Aik. This Aik is scattering amplitude or amplitude of scattering of the ith particle. So this amplitude part can be expressed by equation number 33, that is Aik is A0 e to the power ik. So L, which is a function of k, is the mod A0 square summation I is 1 to n e to the power I k dot r1 summation I is 1 to n e to the power minus ik r1. So this is A0 mod square summation this e to the power ik ri minus rj. And in turn we define a quantity called structure factor by SF. One is correlation function CF and this is structure factor SF. This one, and for n particle system we say this is static structure factor, that is SK, equation 14.35, 1 by n summation I is 1 to n summation j is 1 to n e to the power ik ri minus rj. So what is significance of this static structure factor? This indicates the structure factor are related with pair correlation function. Hence, this, after defining the static structure factor, we will correlate the, we will connect this with the thermodynamic variables. What are our thermodynamic variables? That is internal energy UR. How related? UR is 3 by 2 nk beta T plus n rho phi r g r 2 pi r square into dr. Similarly, the Hamiltonian, which is p square by 2m plus your potential function phi, are related to the canonical partition function and your microcanonical partition function. How Now the canonical partition function in this case is canonical part Zn, that is integration d to the power minus phi by k beta t dqr1 dqr2 dqrn. So the probability of getting, if you consider number of weights getting n molecules out of n volume elements dqr1 dqr2 up to dqrn, then you have n factorial into n minus n factorial. So probability of getting n minus n molecules is Zn inverse integration up to e to the power minus phi by k beta t dqrn plus 1 up to this. So rho n, this factorial is m by n minus n factorial e to the power minus phi by k beta t, and so and rho n dash is n by v. Now the internal energy is E is equal to k beta t square del log qn by del t. So the total energy is 3 by 2 n k beta t, and 1 by z, this factor becomes equal to 3 by 2 n k beta t plus n1 phi r gr 2 pi r square into this. So this clearly indicates we can calculate the pressure, whose value is k beta t d log ln q by del v. So from the structure factor and correlation factor, we are obtaining the expression of that is pressure of thermodynamic system, that is the partition function of microcanonical ensemble. Then partition of canonical ensemble Qn is Vn by n factorial lambda to the power 3n integration 0 to 1 e to the power minus phi by k beta t. Hence, you can obtain the final expression for pressure is P is equal to rho k beta t 1 minus rho by 6 k beta t integration r d phi by dr. So what we got in this chapter? Can we summarize? That we have calculated we can measure the fluctuation delta x in terms of delta x by x square average. And the laws of thermodynamics are valid when r is very small, and for grand canonical ensemble and microcanonical ensemble, it is difficult to calculate the correlation function due to large amount of fluctuations. And the correlation function is defined by the equation GRR dash in terms of Green's function, like NR minus NR average into NR dash minus NR dash average. The correlation function GR minus R dash is N D3R minus R dash plus N D3 R N square gamma R minus R dash. And the correlation length of the nearly 37% times the actual value of r. Then we calculate the integral function, and the scattered wave is represented by Lk A0 square summation L I is 1 to n, j is 1 to n, e to the power I this one. For a Gi number of for a Gi, the internal energy is 3 by 2 nkt n phi phi r gr 2 pi r square dr. Now, when we know the scattering, then how the phase transition occurs? Next question of discussion is how phase transition occurs. So we have first order phase transition as per your chapter 15. Phase transitions. Then we say what is phase transition? We can classify phase transitions. We will show phase diagram. Then we will discuss first order phase diagram and second order phase diagram. Okay. Then we will discuss cooperative phase change. What is phase transition? The first point is, what is phase transition? Phase means solid, liquid and gas. Phase transition means when a solid changes to liquid during the transition point from solid to liquid or gas, or area basis in case of plasma, each element of that state of matter undergoes a transition from one phase to a specific condition which is being governed by temperature as well as pressure. So the roots of phase transition can be traced by intermolecular interactions. Let us have some examples. Suppose 1 kg of water is converted to 1 kg of steam at 100 degrees centigrade. So 1 kg of water at 0 degree will go to 1 kg of water at 100 degree. Then 1 kg of water at 100 degree to 1 kg of steam at 100 degree. And latent heat of vaporization of water is 540 kilocalorie by kg. When this case occurs, then you apply first law of Thermodynamics during phase change. Suppose dQ is total amount of heat energy supplied for phase transition from one phase to other phase, one state of matter to other state. du is internal energy and work done is dW or PdV. You recall first law of thermodynamics, which will arrange dQ is du plus PdV. So in this process, you calculate what is the phase change required. The dV change in volume requires 1607 kilocalorie per gram, and work done will be 40 kilocalorie per gram, which is equivalent to a supplied amount of heat. Hence, this is a mere calculation example. But what is mathematical definition of phase transition? In order to define that, we have to take help of the thermodynamic variables. Which thermodynamic variable? First one is Helmholtz free energy function, and gives potential G. Then A is related to U minus Ts. T is temperature, S is entropy. Then gives free energy function U plus Pv minus Tm. From first law of thermodynamics, dA is du minus Tds minus SdT. Then dG is Vdp minus ST. If we consider the higher order derivative, then we cannot calculate the higher order derivative which does not exist. That means we say that will be 0. We say the higher order, this is the system undergoes a phase transition when the higher order derivative does not exist. Let us take another example, a magnetic system. Let us consider a magnetic system, and the constant parameters are pressure, volume and temperature. So, when du is Tds and H is the external magnetic field, and the magnetization is M, the small magnetization dm. So du is Tds plus Pdv jagare. In case of Pdv, we use HdM. Here V changes to M, P changes to H. So du plus Tds, plus say ydx. Here instead of HdM, we write ydx because y is intensive parameter for magnetic system, and in this case the potential A, which is a function of Tx, is U minus Ts and G is U minus Tx plus Vs. Hence, you derive the extensive variable S as del A by del T and Y as del A by del X. Now, we will classify phase transition, first order phase transition, second order phase transition. How? If during phase transition, the first derivative of the thermodynamic potential is discontinuous for some values of these parameters, and the second derivative does not exist, we have first order phase transition. Remember, when we say the phase transition is first order, now the first derivative of the thermodynamic potential is discontinuous and the second derivative does not exist. First derivative of thermodynamic potential is discontinuous and the second derivative does not exist. Then we say this is first order phase transition. Now, for the result, we can say del by del T del G by del T is equal to the phase transition of a magnetic system we have considered. You can see del by del T of this is minus ds by dt. Now, del square G by del second order is minus Cp by T. Cp is heat capacity at constant pressure. This relation suggests second derivative of Gibbs potential is negative. So, G versus T curve gives a bell-shaped curve, this type of curve. So, this is first order phase transition. And this is G versus T curve. This is a continuous phase transition. So, these two curves indicate that we have two types of phase transition. First order, where first derivative is discontinuous and second derivative does not exist. If it does not occur, then this is second order phase transition. But we can classify the phase transition based on the symmetry. We know a substance, liquid or gas phase has isotropicity. That means it undergoes rotational symmetry. That means each particle undergoes rotational symmetry. Hence, during liquid gas transition, there is no change in symmetry of the system. So, we have different phase diagrams. Suppose this is a diagram between pressure and temperature. S stands for solid, L liquid, G gas, this is triple point, this is Hoare-Post line, this is fusion line, and this is vaporization line. You have read in +2 stage. And this phase diagram clearly indicates that the triple point is purely geometrical concept where TA, TB and TC lies in equilibrium. That is your triple point. And you can say when solid changes to liquid or liquid changes to gas or solid changes to gas, these three states, gas, dg, dp is 0 and dg is equal to 0, dt is equal to 0. Now S1 plus lambda S2 will be 0 and lambda is an arbitrary constant. Now Gs minus Gl is 0, Gl minus Gg is 0. So Gs minus Gg will be 0. These three curves, when a gas at the solid, G of S, G of G gas and G of L liquid, that becomes equal to 0. So at the triple point, the triple point represents the point where three states of matter coexist in thermal equilibrium. Let us take an example of an isothermal real gas. We know van der Waals gas, how it deviates from real gas. This is the curve. This is a PV diagram where we have found the pressure and volume are divided by critical pressure and are related to critical pressure, critical volume and critical temperature. PC, DC and TC. and at the point of inflection you will find these three curves indicates that when T is Tc or when V is less than Vc or P is less than Pc, then the phase transitions becomes very different to understand. When you increase the pressure, the condensation of liquid starts, and this indicates zero of liquid phase. Then after that, no further transition takes place and corresponding temperature is critical temperature, corresponding line is liquid vapor line. This was taught in your +2 stage and +3 stage phase transition in thermodynamics. Then what is mathematics for first order phase transition? We have to consider a Helmholtz free energy function A and Gibbs potential G. G is your Gibbs potential. Take the same equation. dA is minus PdV minus SdT. dA is minus PdV minus SdT. G is VdP minus SdT. VdP minus SdT. Then we shall do dA by dt, dV at constant temperature is minus P. dG by dt, dP at constant temperature is V. dG by dt at constant pressure is minus S. So these are the four equations derived from this one. That means these are two equations for Helmholtz free energy and Gibbs potential. First derivative exists. It indicates the entropy changes discontinuously as a function of temperature at the transition point. Now volume changes as a function of pressure at the transition point. And for an isothermal case, dt is 0, and an isobaric case, dP is equal to 0, the process dG is equal to 0. So this is the phase change diagram when it moves from first stage to second stage. And in some cases, the S versus T diagram looks in this manner. The third diagram, you can find the variation. This is variation of entropy versus temperature. First one is Gibbs function versus temperature. Next one is volume versus temperature. These three phase diagrams leads to Clausius-Clapeyron equation of phase change. You have read Clausius-Clapeyron equation, that is dP by dt is L divided by T into V2 minus V1, where dP by dt change in pressure with respect to temperature, L is the latent heat, T is the temperature, V1 and V2 are change in volume. And this Clausius-Clapeyron equation is also called fast latent heat equation. To obtain derived Clausius-Clapeyron equation, we have derived in thermodynamics from Maxwell's thermodynamic relations TV St del T by del V TV Sp is equal to del S del P by del S, and so minus sign. There are four Maxwell's equations. You derive the Clausius-Clapeyron equation. But here we define since we defined the Gibbs function, so dG is equal to 0, and the phase transition from 1 to 2 state is governed by this equation V1 dP minus S1 dP is V2 dP minus S2 dP. So S2 minus S1 into dt is V2 minus V1 into dt. And dP by dt is S2 minus S1 by V2 minus V1. So during phase transition, the temperature remains invariant, and the difference in specific entropy becomes S2 minus S1 is L by T. So H2 minus S1 is L by T, dP by dt is L by T into V2 minus V1. So this is represents the equation of liquid to vapor or solid to liquid, that is either for fusion or for sublimation. Now we will focus our attention on second latent heat equation. So first latent heat equation is your Clapeyron equation. Now the second latent heat can be obtained since we know S2 minus S1, this factor S2 minus S1 is equal to L by T. So if you take a differentiation with respect to temperature, again d by dt of L by T, this will be ds2 by dt minus ds1 by dt. Then 1 by T del L by del T minus L by T square. Here T is constant, differentiation of L. Here L is constant, differentiation of T with respect to T, 1 L by T square is ds2 by dt minus ds1 by dt. When you multiply T, del L by del T minus L by T is T del S ds2 by dt minus T ds1 by dt. So del L by del T is minus L by T is C2 saturation, this one, minus C1 saturation. This is called second latent heat equation. And you note this equation, from this equation we can calculate the specific heat of saturated vapor. What is that one? That is C2 saturation minus C1 saturation. That means the amount of heat required, the temperature of unit mass of a saturated vapor through 1 degree centigrade is known as your heat capacity of saturated vapor pressure. When you make an analysis how this specific heat changes when pressure of the vapor and does some external work, whether the energy appears from inside and it raises the temperature. Let the amount of energy generated is Q1 and Q2 is the amount of heat required to raise the temperature through 1 degree centigrade. Now three conditions arise, whether Q1 is equal to Q2, Q1 is less than Q2 and Q1 is greater than Q2. When Q1 is equal to Q2, the total amount of heat required is equal to heat of compression of the vapor. Remember, when Q1 is equal to Q2, the heat required is equal to the heat of compression of vapor. So no net heat is supplied to the system, first case. Second case, when Q1 is less than Q2, total, that means total heat required to raise the temperature of vapor through 1 degree is more than the heat of compression. So net amount of heat is supplied to the system. Q2, no net heat is supplied. When Q1 is less than Q2, you can say net amount of heat is supplied to the system. As a result, the specific heat capacity becomes positive. When Q1 is greater than Q2, this is an interesting fact that the total heat required to raise the temperature of vapor through 1 degree is less than the heat of compression. So some heat is removed and the vapor is constructed to have negative heat capacity. Okay, this is all about the first order phase transition. Then we will focus on second order phase transition, and we will discuss the Ehrenfest theorem. We will derive the Ehrenfest equation from it. So what is mathematics of second order phase transition? This first order phase transition arises due to discontinuity. Second order phase transition arises due to continuity. And it is characterized by continuity of Gibbs potential. First thing, due to continuity of Gibbs potential, second order phase transition arises. Second point, in second order phase transition, there is a finite change in entropy. Entropy as well as volume at transition temperature T is equal to Tc. And during this phase transition, let us have an example. Say liquid changes to helium. When liquid in a particular case, the phase transition takes place in a liquid helium, the Gibbs potential, entropy and volume remain same. But there is a discontinuity in heat capacity. So the entropy remains constant. The second order derivative undergoes a discontinuity during transition of phase transition. If you look at the Clausius-Clapeyron equation, which suggests dp by dt is equal to L by V into S2 minus S1, the Clausius-Clapeyron equation you have read, our first latent heat equation, that is dp by dt is L by T into V2 minus V1. If you focus on this equation, then you will find the dp by dt becomes indeterminate because L by T takes into V1 minus V2 takes 0 by 0 form. So we graphically represent the phase first order, second order phase transition like this. This is G versus T graph. This is S versus T graph. S is your entropy. This is volume versus temperature graph. This is specific volume, specific heat versus temperature graph. So this is a variation of Gibbs potential. Graphical represents second order phase transition. And this is a transition from phase 1 to phase 2. This is a transition, this is the dotted line, this is a transition, the same thing, G versus T, this is versus temperature and this is versus pressure. The graph in this side stands for variation with temperature in second order phase transition. That is variation of G Gibbs potential, entropy, volume and specific heat at constant pressure. This is a such variation at constant pressure. Now these are type of second order phase transitions. Then we will focus on Ehrenfest equation. So while deriving Clausius-Clapeyron equation, we used the continuity of Gibbs potential. But in case of Ehrenfest equation, we assume continuity of its first derivative. So if we let us assume two specific entropies, that is S1 is equal to S2 at temperature T. When there is a variation of temperature, T changes to T plus dt, you will find the entropy of the first system changes to S plus ds1 and second system changes to S2 plus ds2. When T changes to T plus dt, pressure changes to T plus dt, S1 changes to S1 plus ds1 and S2 changes to S2 plus ds2. Since S1 plus ds1 is S2 plus ds2 and S1 is S2, this indicates ds1 is equal to ds2. So we can say entropy, specific entropy is a function of temperature and pressure. Now ds can be written as delta S by del T. ds is del S by del T into dt plus del S by del P into dP. Now, using Maxwell's thermodynamic relations, ds can be written as Cp by dt minus del V by del T at constant pressure into dP. So ds can be written as Cp by T into dt minus V alpha dP. So Cp is equal to T del S by del T at T and alpha is 1 by V del V by del T at T. So ds1 is equal to minus Cp1 by T dt minus V alpha 1 dP. ds2 is Cp2 by T dt V alpha 2. So when you put this, ds1 is equal to ds2, so right hand side RHS of 32 and 33 becomes equal, which gives you, after simplification, we are able to calculate Ehrenfest's equation. That is dP by dt, change in pressure with respect to temperature is Cp2 minus Cp1 by T into V alpha 2 minus alpha 1. The change in temperature dP by dt is Cp2 minus Cp1 T V of alpha 2 minus. Now, you can calculate using this Ehrenfest equation, you can estimate what is dP by dt when helium, liquid helium, undergoes state 1 to state 2, and you can find the value. If you calculate, then dP by dt will be around 79.4 atmospheric pressure per Kelvin. So we suggested that the phase transitions which are described here can be used to change, it can be applied in magnetism. That is, when ferromagnetic substance changes to paramagnetic substance, we have read an equation that is Curi's temperature law, that is susceptibility, and Witt's law. Susceptibility is inversely proportional to temperature. When a temperature increases, susceptibility gradually decreases. When susceptibility decreases, ferromagnetic susceptibility attains paramagnetic susceptibility. In that case, there is a phase change occurs in magnetism. So these are treated as second order phase transitions. Now there is one heading, cooperative phase transition. When cooperative phase transition occurs, we know energy of weakly interacting systems can be broken into individual particles. So the partition function of the system is the product of several partition functions. That means Z is equal to product of Z1, Z2, Z3 up to Z. So the becomes very strong enough, then decomposition takes place and system becomes strong interactive system. And in a strong interacting system, thermal excitation takes place due to mutual cooperative action between the constituent particles. Remember, when system is weak, when you calculate its partition function, this is weakest. But when you consider all the particles of the system and multiply, this becomes largest, the energy becomes more, this is strongly interacting system, and there is a mutual cooperation action between the constituent particles. And in this case, we define the function known as we define the word cooperative phase transition. Example is, consider iron-like substances, iron, nickel or cobalt-like substances, say ferromagnetic substances. We know the ions at the adjacent sites of ferromagnetic substances are parallel at a very low temperature. Due to exchange of interaction, you can find, or when the Curie temperature it attains, then the susceptibility changes, as a result of which the specific heat capacity changes. So there is a quick and continuous decrease in degree of ordering, and at critical temperature, this cooperative transition takes place. We can apply Heisenberg model or exchange interaction model of Heisenberg to describe such systems. Here we do not have complete statistical review of this. Then in this chapter, what we have read in a summary, every substance undergoes transition from one stage to other stage, and the cause of phase transition is intermolecular interaction by attraction or repulsion. Phase transition can be classified on the basis of Helmholtz free energy and Gibbs potential, as well as on the basis of symmetry. The third conclusion is the first order derivative of Gibbs potential, like volume and entropy, changes discontinuously during phase transition. Then this is first order phase transition. And second order derivative does not exist. During liquid gas phase transition, there is no symmetry is maintained, but transition of paramagnetic to ferromagnetic substance, the pattern symmetry changes. A phase diagram is generally two-dimensional plot with the axis representing two thermodynamic variables. Next is, in the isotherm PV diagram, the point of inflection, which curvature 0 corresponds to critical temperature. With this symbol, you can derive Clausius-Clapeyron equation dP by dt is L by T into V2 minus V1 in first order phase transition, and second order latent heat equation is del L by del T is equal to minus L by T is equal to C2 saturation minus C1 saturation. Then you can have Ehrenfest theorem equations, that is dP by dt is Cp2 minus Cp1 Pv alpha 2 minus alpha 1, and dP by dt is alpha 2 minus alpha 1. Then we discuss cooperative phase transitions. Next course of discussion is second order phase transition. In case of second order phase transition, what we find the second order phase transitions or phase transition 2, we will discuss the quantum mechanical view. We will consider the spin, that is this phase transition 2, that is your Ising model. We will discuss one-dimensional Ising model. We will apply the perturbation method of solution, the quantum mechanics. Then we will discuss 2D and 3D Ising models. Then we will discuss Briggs-Williams approximation, mean field approximation, order parameters, critical exponents, and the rudiments of Landau model of phase transition will be discussed. So, first important one is Ising model. Ising model always asks in the examination. Here we deal with the exchange of integrals or exchange of spins. We know in Heisenberg's exchange of interaction, where we use the, suppose we take an example of a ferromagnetic substance. We assume that the and significantly apply. As a result, we consider the transition proposed between two ions. We consider two ions, Ising model, say I and J. And spin of ith ion is Si, spin of jth ion is Sj. So when there is a exchange of energy between ith and jth particle, we can say E exchange is minus 2J times Si into Sj. Si and Sj are spins, and between ith and particle having spins Si and Sj, there is a factor J. J is known as exchange integral. And this equation arises due to overlapping of terms. Similarly, when it undergoes exchange with the other particles in one dimension, we can take the summation. We can take the this factor minus 2J Si. We can apply to large number of particles, say Sij into Sjj. As a result, we find this, we explore this to different dimensions, whether the exchange is between one dimension, whether the exchange is between two dimension or three dimension. The first text is Ising model in 1D, one dimension. So first one is, let I and J are Si and Sj, I and J particles, Si and Sj, not spin of I particle and J particles. So corresponding Hamiltonian H can be written as, for n such spins of all particles, is minus H, equation 16.2, I is from number of particles 1 to n, Si minus J, summation Si plus 1. And here Si take integral values, that means plus 1, minus 1, so on. And we calculate the external magnetic field by a factor small h. This factor suggests this is half mu0 times. Mu0 is magnetic moment. H is the external magnetic field. Here, H is not Planck's constant. H is a factor, okay, which calculates the external magnetic field or make a relation between magnetic moment and external magnetic field. Here, the term, you can say the half appears because of interaction energy is half. Now you can apply perturbation theory perturbation theory, quantum perturbation theory of spin half particles to describe this Ising model. We consider the Hamiltonian H is equal to H0 plus H1. What is H0? This is Hamiltonian minus H is, we have defined a factor which is half of mu 0 H and a sum over n number of particles Si. And H1 is equal to minus J summation I is 1 to n Si plus 1. Here H0 does not contain any interaction. So single partition function will be Q0, that is sum S, which takes integral values plus 1 minus 1 e to the power beta Hs. H is small h is already defined, and Q0 will be e to the power plus beta h for h s is equal to plus 1, and for s is equal to minus 1 e is minus beta h. Or you can say Q0 is, for this form is nothing but hyperbolic cosine hyperbolic function, so 2 cos hyperbolic beta x. Now the partition function z to the power n can be written as Q0 to the power n, which is 2 times cos hyperbolic function, and the expectation value gives rise to, under perturbation correction, Si0 is tan hyperbolic beta x. When you consider the interaction term, SISJ is Si0 Sj0 for I is not equal to j. And the Hamiltonian, perturbed Hamiltonian becomes minus Jn tan hyperbolic square beta x. So the second order perturbation term here we find here Hi square average is j square I is 1 to n j to n Si plus 1 Sj plus 1. So the first order possibility is I is equal to j, then h1 square for I is equal to j is the average of Si square Si plus 1 square. So Hi square at 0 I is equal to j is equal to 1. Now, when you simplifying these equations, we can obtain H1 approximation square the minus j square n plus 2n tan hyperbolic square beta x plus n square minus 3n tan hyperbolic to the power 4 beta x. Then log z is log z0 minus beta h1 plus beta square by 2 h1 average of h1 square minus h1 average square. Hence the potential we obtain, Helmholtz free energy potential A is equal to minus 1 by beta log z. If you put the value of z, then you will calculate the log z at h is equal to 0 is n log 2 plus b square j square by 2. So the energy of the system E is equal to minus del log z by del beta, that is minus n beta j square. So what does it implies? It implies the contribution. We have taken zero magnetic field. So the contribution of energy can form the second form of this equation. And the approximate method, we can got the indication about expansion of ferromagnetism using this Ising model. And this solution can be obtained by variational principle, which indicates about ferromagnetic transition below classical temperature. You can have a direct method for this one. That is, Z is equal to, you consider directly H is minus H by 2 Si I state plus Si plus 1 minus J summation I is to n Si I plus 1. So the canonical partition function Z is equal to exponential of this one beta summation I is 1 to n H by 2 Si plus Si plus 1 plus Js1 into this one. We can write the powers of exponential SI is plus 1, then SI average is either 1 or 0, or SI minus 1, this SI ket is 0, 1. This is a Pauli spin form a Pauli spin matrix, that is sigma z is 1 0 0 1. So we arrive that Sk is equal to the average of Sk sigma z Sk, and the value can be written, the trace of this is given by e to the power beta h plus beta z by e to the power minus beta z, e to the power minus beta z. This is this stands for the trace of this matrix. T and stands for or transfer matrix. And the partition function z, finally you will find the partition function is S1. This is some other method, trace of this transfer matrix, which is trace of the transfer matrix written here. So in this manner we can discuss the second and third Ising model. For second and third Ising model, 2 and 3 dimensional arrays are considered, and we consider the Hamiltonian of the system. The Hamiltonian is given by minus h summation I is equal to n si square minus j si minus sj square. We consider the magnetic field in z direction. As a consequence, we take their interactions into account. When you take the composite speed, in case of one dimension, we shall take into consideration the nearest neighboring interaction only. But when we observe the second Hamiltonian, we note that partition function is represented through a component. This is used in second and third order Ising model. Then we will consider Bragg-Williams approximation. This approximation talks about a coordinate number among the nearest neighbors, and it depends on the nature of the lattice. Say for one dimensional lattice, the coordination number Cn is equal to 2. For two dimensional square lattice, it is 4. So we define the average spin or expectation value of the spin R is S cap 1 by n summation I is 1 to n Si square. Here we have bothered, but for second term we introduce approximation, that is called Bragg-Williams approximation. So the Hamiltonian of Bragg-Williams approximation will be minus h summation I is 1 to n Si square minus j sum over ij s. Here n is quite large. We may ignore the boundary effects, which much loss generally take number of nearest neighbor pairs as half NQ. So E can be written as minus NHR minus half NQ JR square. As a result, N2 becomes equal to N by 2 into 1 plus or minus R. Now we can recall the combination or the what is the configuration of this one, this combination N1 and Ns. This NNS is equal to n factorial by n plus factorial into n minus factorial, and corresponding partition function will be z is equal to n factorial by n by 2 into 1 plus r factorial 1 minus r e to the power beta n hr plus q by 2 jr square. Now we will consider this approximation to calculate the mean field. To calculate the two-dimensional Ising model, we can extend it to two-dimensional square lattice, and this approximation is basically used to explain the existence of ferromagnetic phase transition in a qualitative manner. Then another approximation is mean field approximation, when you consider this approximation, Bragg-Williams approximation, BW approximation. Then the another approximation is mean field approximation. Here we consider the mean value of this field. So in a BW approximation, we overcome the errors by mean field approximation, and the Hamiltonian is described minus h summation I extends over all the particles for j and is only the nearest neighbors, and there is a factor half which appears in the second term. This is half arises due to doubly counting. So the Hamiltonian is minus h I is 1 to n Si minus j by 2 I is 1 to n j is 1 to q Si Sj. And we write the Hamiltonian h is equal to minus h Si j Si sum over j is 1 to q Si, such that j by 2 Sj is hmf. Here mf means mean field approximation. When we put this value, the Hamiltonian takes the form h is minus h plus q h mf Si. Now you can apply this to canonical partition function z, which is 2 cos hyperbolic beta h plus q h meaning your mean field approximation, and you got mean field Hamiltonian. So in case of BW Williams approximation, you have He plus H Q H MF, and here H is He minus Qj by 2 tan beta hyperbolic this one. Now we have an order parameter. What is order parameter? This order parameter is used in symmetry breaking cases. That means when phase 1 and phase 2 transitions, there is a symmetry breaking, and there is a non-zero order parameter. For example, there is a spontaneous magnetization. When spontaneous magnetization is 0 in the paramagnetic phase, but non-zero in ferromagnetic phase. So spontaneous magnetization is an order parameter. Remember, spontaneous magnetization is 0 in paramagnetic phase, but non-zero in ferromagnetic phase. So spontaneous magnetization is called an order parameter in magnetic phase transition. So if we have a element G of the group, then GH inverse is equal to H. We define this spontaneous order parameter of phase transition for a disorder phase. For a disorder phase, we use this spontaneous phase transition, and we define G brass I is equal to brass I. Similarly, if the group element is H dash, then H dash brass I dash is equal to brass I dash. So the elements belonging to G, but outside G, we get H dash minus 1. Here brass I is not equal to G. As a result, the average of psi dash H1 minus 1, H dash minus 1, H psi is not equal to 0. So, what is critical exponents? Critical exponents in various thermodynamic quantities, there are power law behavior. So we imposed for a function considering thermodynamic f is fxy, we define x is positive, so fx, x becomes 0 at the critical point, and the power law behavior then stipulates the example of following limit. Limit x tends to 0, log fx by log x is lambda. Lambda is a constant, and this is lambda is a constant. Then we can define the critical exponents to explain such behavior. So one is, suppose, let us take an example, fx is ax square. For small x, the leading term fx is same as ax square. So we can write fx is equal to ax to the power lambda into 1 plus 1, where the dot stand for it goes to 0 or limit extends to 0. So we can say fx is the order of x to the power lambda. If we say the critical exponents of many possible functions and T is temperature, Tc is critical temperature, then we can define a dimensional variable T is equal to T minus Tc by Tc. When T is equal to Tc, this variable tau, dimensionless variable, plays very important role, and it has power law behavior. Potential A is T to the power 2 minus alpha for tau greater than 0, and minus tau square minus alpha when tau is less than 0. So the free energy function becomes an intensive parameter out, and the temperature becomes an extensive variable. What is rudiments of Landau model of phase transition? When we identify the order parameter without any microscopic phenomenon, without worrying about microscopic phenomenon, we discuss magnetic phase transition. And what are the assumptions? The OP. OP means order parameter is M, whose value is 0, first assumption. Our focus is on vicinity of critical temperature of M. The free energy A is represented by a constant term plus AM square plus BM4 plus O to the power M6. That means when M tends to M, the constant is hardly relevant and it may be equal to 0. And the series, this series is truncated when there is a physical explanation is captured, that is A is minimum, del A by del M is equal to 0. So M0 is 0, and you calculate M0 may be plus or minus root 2 over minus A by 2, such that AT is T minus Tc and AT may be A0 into T. Now, the asymptotic behavior of free energy can be written in this manner: A is K0 plus AT Tm square B0 m to the power 4. The variation can be written this form of a graph. The coefficient of power series for tau is greater than 0, AM0 potential versus M graph. This is tau is equal to 0 and this is tau less than 0. This is how they varies the magnetic states, varies magnetic moment, varies with this value, and this is maximum when M is equal to 0. This indicates a maximum value. So we conclude the critical exponents are implied form of power series. This Landau conclusion. A free energy expansion is constructed on the symmetry grounds. The critical exponents are continuous during phase transitions. Hence, in this chapter, we discuss the phase transitions, we discuss the Ising model, and we focus on the different type of Ising model. Then we have two type of approximation, BW approximation and MH approximation. Then we discussed Landau model. Thank you for patience of hearing. Thank you. Let us close here.
Thank you. Hello.
Hello.
Hello. Hi, Shivram.
Hi.
You are from?
From Ganjam.
Where are you from?
Ganjam, madam. And you?
अच्छा ओडिशा गंजाम.
Uh, where are you from?
खोर्धा.
Uh,
गंजाम माने बरहमपुर ना कोई जगह?
हाँ बरहमपुर दिगपहंडी गोकर्णपुर.
କ୍ଲାସ୍ ଭଲ ଲାଗୁଛି?
କ୍ଲାସ ଟା ଖାଲି ଆମେ ତ ପଢି ପାରୁନେ ଯେ
ଟିକେ ଯାହେଲେ ବି ଗୋଟେ
ଅଲଗା ହଉଛି.
ଇଣ୍ଟରାକ୍ସନ ହଉଛି, ଗୋଟେ କିଛି ବୁଝା ହଉଛି, କୋଉଠି କଣ ଅଛି ଜଣା ପଡୁଛି.
ତାପରେ ଆମେ ଅଲଗାରେ ବସିକି ପଢିବା ପାଇଁ ଇଏରେ ଆଉ ନାହିଁ.
ଟାଇମ ନାହିଁ ଆଉ.
ଫ୍ଲୋରେ ଚାଲିଛି ତ ପୋଷ୍ଟଟା ଓଲଟେଇବା କଥା, ସେ ବି ଆମେ ମଝିରେ ମଝିରେ ସେ ପୋଷ୍ଟର ସେ କୋଉଠି ପଢଉଛନ୍ତି ନା ସେଇଟା ଦେଖିବି ହଉନି. ତାପରେ
ଦେଖି
ସେ
ହଉନି
ଟାଇମ୍
ଯେ ଏବେ
ଦେଖିଲା
ଟିକେ ସ୍ପିଡରେ ସେ ଯାଉଛନ୍ତି, ସ୍ପିଡରେ ନିଜକୁ ଯିବାକୁ ପଡୁଛି.
ଆଜ୍ଞା.
ଏବେ ଆଉ ଆପଣଙ୍କର ଷ୍ଟଡି ସେଣ୍ଟର କୋଉଠି?
ଆମର ପୁରୀ ମ୍ୟାଡାମ.
ପୁରୀ.
ଆପଣଙ୍କର?
ଏଇ ବିଜେବି ଏଇଟା ବିଜେପି କଲେଜ.
ଆପଣ ଖୋର୍ଦ୍ଧା ତ ସେଇଠି ପାଖ ଦେଇ ଦେଇଛନ୍ତି, ଆମର ଏପଟେ ଷ୍ଟଡି ସେଣ୍ଟର ନାହିଁ ସାଇନ୍ସର। ସେଇଠି ପୁରୀରେ
ଆମର
ହିଁ ଥିଲା, ମୁଁ ଏଠି ଖୋର୍ଦ୍ଧା କରିଦେଇଥିଲି ଭଲଥାନ୍ତା। ଭୁବନେଶ୍ଵର ଖୋର୍ଦ୍ଧା, ସେଇଠି ବି କ୍ଲାସ କରିବା ପାଇଁ ପଚାରିଲୁ ଯାଇକି। ବୋଲେ ଆମର ତ ରେଗୁଲାର କ୍ଲାସ ପାଇଁ ଷ୍ଟାଫ ହଉନାହାନ୍ତି, ଆଉ ତମକୁ କିଛି ଟାଇମ ଦେଇ ହବନି, ଆପଏଣ୍ଟମେଣ୍ଟ କଥା ମଧ୍ୟ ହେଇପାରିବେନି ବୋଲି କହିଲେ।
ତମର ଏଇଟା ଇଏ ଆସିଲାଣି କି ଆସାଇନମେଣ୍ଟ ମାର୍କ ଆସିଲାଣି?
ଇଏ ଆମର ଆସାଇନମେଣ୍ଟ ସବୁ ସବମିଟ କରିଦେଇଛୁ ଦୁଇଥର, କିନ୍ତୁ ଏଥର ଆମେ ଫର୍ମ ଫିଲଅପ୍ ଟା ସେକେଣ୍ଡ ଇୟର ସବୁ ଯାକ କରିନଥିଲୁ।
ତମର କୋଉ ବ୍ୟାଚ୍?
ଆଜ୍ଞା 2024
ଜାନୁଆରୀ 24 ନା?
ଆଜ୍ଞା ଜାନୁଆରୀ 24।
ସେମ୍
ଆପଣ
ବ୍ୟାଚ୍,
ଆଜ୍ଞା
ମୋର ବି ସେ ଜାନ 24।
ଆଜ୍ଞା ଆଜ୍ଞା।
ହୁଁ।
ଆଉ ଇଏ
ଆଉ କଣ
ଆପଣ
ଥିଓରି
ରେଭେନ୍ସା
ଭଲ
ଇଣ୍ଟରନାଲ?
ମାର୍କ ଆସିଛି, ଯୋଉଟା କ୍ଲିୟର ହେଇକି ଯାଇଛି?
ନାଇଁ ମ୍ୟାଡାମ, ମୁଁ ତ ଫିଜିକ୍ସ ପାସ ରେ ଥିଲା, ଅନର୍ସ ବି ନାହିଁ।
ଆଚ୍ଛା ଆଚ୍ଛା।
ଏତେ ଭଲ ମାର୍କ ବି ଆସିନି କିଛି, ଖାଲି ଶିଖିବା
କ୍ଲିୟର ଅଛି କ୍ଲିୟର
ପାଇଁ।
ଅଛି।
ନାଇଁ କେତେଟା ଇଏ ଅଛି, ପୁଣି ଦେଇଦେବା ସବୁ ଯାକ ବୋଲି ଫର୍ମ ଫିଲଅପ୍ କରିବାକୁ ପଡିବ। ଆପଣଙ୍କର ମ୍ୟାଡ଼ାମ?
ମୋର କ୍ଲିୟର ଅଛି, ଖାଲି ଫାଷ୍ଟ ପେପର ଟା ଗୋଟେ ଅଛି, ଆଉ ବାକିଟା ଏଇ 4ଟା ଦେଇଥିଲି। ଆଉ ଏଥର ଦେଇନା, ନେକ୍ସଟ ଟାଇମ ଡିସେମ୍ବରରେ ଦେବି ଆଉ।
ହଁ।
ମ୍ୟାଥମେଟିକାଲ ଫିଜିକ୍ସ ଟା
ଏକ୍ଜାମ
ହଉନି,
କେମିତି
ଯେତେ